Everybody, in this video we're going to discuss the topic number 2 in chapter 4, chemical compounds. We'll first learn how we use the dots to represent the valence electrons for elements, and then we'll discuss ionic and covalent compounds, how we name them, how we come up with the formulas of those compounds. Okay, on this slide, as you can see, that I listed the noble gas core electronic configurations of the first 20 elements in the periodic table. Okay, and here, for instance, for boron, helium, core electrons, the 3 electrons on the 2s and 2p orbitals, they are valence electrons. Okay, so by using noble gas core electronic configuration, we can distinguish the core electrons and valence electrons. In chemistry, in order to visualize those electrons in a better way, we use dots to represent them. For instance, for nitrogen, helium core electrons, 5 valence electrons on the 2s and 2p orbitals, so we use 5 dots to represent those 5 electrons, 1 pair and 3 unpaired electrons. Another example, sulfur, 6 valence electrons on the 3s and 3p orbitals, so we use 6 dots to represent those 6 valence electrons, 2 pairs and 2 unpaired electrons. Okay, another example, argon, 8 valence electrons, so we use 4 pairs, 8 dots to represent those 8 valence electrons. Okay, so this is the dots representing valence electrons. Another reason why we want to show you this is later on when we learn how we draw Lewis structures of chemical compounds, those dotted structures will help us. Okay, how? Well, we will see. Okay, later on in chapter 5 and chapter 6, when we draw Lewis structures, we need to follow some important rules. Okay, the first one is duet rule. Well, for duet rule, it works for hydrogen, helium, lithium, and beryllium, 4 elements. Okay, and for the other elements, okay, at least for the first, for the other elements in the first 20 elements, they follow octet rule. Okay, so let's go through them one by one. For duet rule, that means these 4 elements, they tend to have 2 electrons in the outermost electronic shell. What does that mean? Let me show you. Let's see hydrogen. Okay, hydrogen, if it has 1 valence electrons. Okay, if you provide 1 more electron, it will have 2 electrons outside. Okay, and because it gets 1 more electron now, this hydride, it caused hydride, it's going to be negatively charged, the anion. Okay, so it has a tendency to get 1 more electron to form this paired electron in on the 1s orbital. Okay, but of course, okay, in chemistry, most of the chemical reactions involving hydrogen, most of the time, let me write it here, most of the time it will lose, let me put the plus sign here, just indicate that this is gaining 1 electron. When hydrogen loses 1 electron, then it becomes hydrogen plus. Okay, in this case, of course, there would be no electrons left. Okay, when you form the hydrogen plus. All right, but no matter what, for hydrogen, it can form this hydride with 2 electrons on 1s orbital. Okay, for lithium, well, lithium, you know that it has 1 electron on the 2s orbital. Okay, so let me write it here. For lithium, it tends to lose 1 electron from the 2s orbital to form lithium plus. Okay, so it has a tendency to have 2 electrons on the outermost electronic shell. Remember, shell means the electrons on the same orbitals, on the orbitals with the same principal quantum number n. All right, All right, beryllium. Beryllium has 2 electrons on the 2s orbital, so it tends to lose 2 electrons to form beryllium 2 plus ion. Okay, so in this case, you only have 2 electrons left. Okay, and those 2 electrons for beryllium 2 plus would be on the 1s orbital. How about helium? Well, for helium, if you take a look at the electronic structure, it has 2 electrons already. Okay, so it's happy enough. That's why helium is very, very stable. Does not want to lose electrons, does not want to gain any more electrons. It will stay like 1s2 electronic configuration. Okay, so helium, very stable. That's why we call this whole group noble gas. Later on when we discuss the octet rule, you will realize because neon, argon, krypton, xenon, they all have 8 electrons in the outermost shell, so they are stable. Okay, so all right, duet rule. Now octet rule, similar to duet rule, but this time for octet rule, it has a tendency to get 8 electrons in outermost electronic shell. What do I mean by that? Okay, let's use oxygen as one example. Okay, well, for oxygen, as you notice, it has 6 electrons on the 2s and 2p orbitals. According to octet rule, because it has only 6 valence electrons, it has a tendency to get 2 more electrons from other species. Okay, don't need to care about where those 2 electrons come from. But anyway, so for oxygen atom, it has the tendency to get 2 more electrons to fully occupy the 2p orbitals. Okay, in other words, if you let me write it here, oxygen six valence electrons, it has a tendency to get 2 more electrons. All right, so it can have 8 electrons. Okay, in the outermost electronic shell on the 2s and 2p orbitals. Okay, of course, at this moment you will get O2 minus because you get 2 more electrons. So this is going to generate an anion with the 2 negative charges. Let's see one more example. How about chlorine? Chlorine, it has 7 valence electrons on the outermost electronic shell on the 3s and 3p orbitals. According to octet rule, since it has 7 valence electrons, it has a tendency to get 1 more electrons to get stabilized. So for chlorine, you can obtain 1 more electron to generate chloride. Okay, so for chloride, it has 8 electrons on the 3s and 3p orbitals, so it becomes more stable. So these are the elements that can get electrons to satisfy octet rule. But how about those elements that they have the tendency to lose electrons to satisfy octet rule? No problem. Let's take a look at the sodium. Well, for sodium, it has 1 electron on the 3s orbital, and the core electron is neon. Okay, so for sodium, instead of getting 7 electrons to satisfy octet rule, because it's going to be very hard for you to get 7 electrons in one shot in chemical reactions, so instead it tends to lose 1 electron, and that will be sodium plus. Okay, after it loses 1 electron from 3s orbital, the electronic configuration would be neon. Okay, would be neon. And if you happen to remember the electronic configuration of neon right here, you can see that it does, for sodium plus, it does have the 8 valence electrons on the 2s and 2p orbitals in this case. Okay, not valence electron, but it does have electrons on the outermost electronic shell, which are the 2s and 2p orbitals. Okay, so sodium plus, it becomes more stable. Another example, let's see calcium. Calcium, 2 electrons on the 4s orbital. Okay, so for calcium, it has a tendency to lose 2 electrons from the 4s orbital to become calcium 2 plus. Okay, and when you lose, after you lose the 2s electrons, the electronic configuration of calcium 2 plus would be just argon. And when you look at the electronic configuration of argon, okay, it has 8 electrons on the outermost electronic shell. So calcium 2 plus is stable. Okay, so these are the duet rules and octet rules that we need to follow when you consider whether it's gonna lose or gain electrons. Okay, all right. Now let's take a look at ionic compounds. Here on your right side, these are some important properties of ionic compounds. For instance, for ionic compounds, they always have a positive and a negative ions, okay, 2 parts, like sodium chloride, as the picture shows you. Sodium chloride, the then positive ion would be sodium plus, okay, and for a negative ion would be chloride. And here, calcium carbonate. Let me write it here. Calcium carbonate. Well, the positive ion is calcium 2 plus. Negative ion, carbonate, CO3 2 minus. Okay. All right. So these are the first one. Always have positive and negative ions. Second property of ionic compounds, sum of positive charges should be equal to the sum of negative charges. What do I mean by that? Well, if you take a look at this 2 example, okay, sodium, 1 positive charge, chloride, 1 negative charge. So when you have equal amount of positive charge and negative charge, then cancel each other. So the whole compound remains as neutral. Same thing for calcium carbonate. Calcium, 2 positive charges, carbonate, 2 negative charges. Okay, so when you combine these 2 ions to form an ionic compound, the charge will be canceled. The compound formed will be neutral. One more example, okay, sodium carbonate. Well, when you have sodium carbonate, now as you notice from the formula, it has 2 sodium ions in this molecule, and each sodium is 1 plus, but now you have 2, right? And meanwhile, for negative ion is carbonate, okay, is carbonate. It is 2 negative charges. As you notice that the charge is still balanced. 2 positive charges can also cancel the 2 negative charges, so sodium carbonate remains neutral. Okay, so this is a second property. Now, third property, formulas reflect the smallest whole number ratio of ions. If you happen to remember what we discussed in first topic of chapter 4 regarding empirical formula and molecular formula, okay, we said that empirical formula reflects the smallest positive integer ratio of the atoms in a formula. Well, looks like for ionic compound, empirical formula is the molecular formula. Okay, so for instance, for sodium carbonate, you have 2 to 1 ratio, 1 carbonate, 1 CO3 2 minus. So this 2 to 1 ratio is the smallest integer ratio between the 2 ions. It's this molecular formula is the empirical formula. Okay, because this is the some basic features of ionic compound. Now let's take a look at this table. Okay, in the following slides, we'll see how we name ionic compounds. Okay, and these tables are from your textbook. Okay, and we have some rules for us to follow when we name those ionic compounds. Okay, the first part 1, is going to be about some simple ionic compounds. Cations here, these are some very common cations with just one element. And here on your right, these are just some simple anions with only one element. Okay, and if you take a look at this metals, okay, these are all main group elements. Okay, main group metals. Lithium, sodium, potassium, rubidium, cesium, these are from group 1. Beryllium, magnesium, calcium, strontium, and beryllium, these are from group 2. And aluminum, group 3. Okay, so you can see that because of the either duet rule or octet rule, all of them lose the electrons, either 1, 2, or 3, to satisfy the either octet rule and duet rule. Okay, for group 1 elements, they tend to lose 1 electron to become more stable. For group 2 elements, they tend to lose 2 electrons to become more stable. Okay, and aluminum group 3, it tends to lose 3 electrons to become more stable. Octet rule. And here, these are some other ions from transition metal groups, but they are not required. Okay, those elements and ions and their names highlighted by the red square, they are required. Okay, if I give you this ion, I need you to know their names. Okay, if I give you the names, I expect you know the corresponding charge and chemical symbol. All right, this table, from the nonmetals, okay, as you notice, the fluorine, chlorine, bromine, iodide, these are from group 17. Because they have 7 valence electrons in the outermost electronic shell, they tend to get 1 more electron to satisfy octet rule. So all of them, most of the time, they'll become anions with 1 negative charge. Oxygen, sulfur, group 16, they have 6 valence electrons in the outermost valence shell. So they have a tendency to get 2 electrons to become anions with 2 negative charges. And nitrogen, group 15, 5 valence electrons, so it has a tendency to get 3 more electrons to satisfy the octet rule. Okay, N3 minus. Again, names, symbols, they are required. Okay, those highlighted by red square, they are required. Okay, let's just talk about some examples. Okay, for instance, NaF. Okay, well, how do we name this compound? According to the rule here, for Na, since it's Na plus, sodium, name of the cation metal, okay, name of the cation metal, name, and the base name of anion, okay, so plus IDE, okay, so it essentially this part. Well, F minus would be fluoride in this case, so the name of this ionic compound would be fluoride. Okay, this is the sodium fluoride. Let's see one more example. How about this one, K2S? Well, K, as you notice, it's going to be potassium. S, sulfur, get 2 more electrons from 2 potassium. It becomes a sulfide. So for the K2S, it would be potassium. Sulfide. Okay, sulfide. All right, let's see one more example. How about this? AlCl3. Well, Al aluminum, Cl, chloride, okay, chloride. So the name of this compound would be aluminum chloride, okay. So this is how we name the ionic compounds. One thing I do want to mention here is when you write the formula of the ionic compound, you do have to consider the charge. Remember the second property of the ionic compound in the previous slide? The sum of positive charged ion, okay, should be equal to the sum of the negative charged ion. Okay, here this is exactly the same thing for aluminum chloride. Aluminum 3 plus, okay. If you got confused about how I come up with this formula, well, you can write the two ions separately. Aluminum 3 plus, chloride 1 negative charge, okay. So remember, if you let those two ions combine to form an ionic compound, the products, the formed molecule or the formed compound should be neutral. Okay, so that means for the 3 positive charges from aluminum, you need to have 3 chlorides. Okay, to balance the 3 positive charges. And when you have 1 aluminum 3 plus and 3 chloride, okay, so when you write the formula, it would give you this. Okay, these 3 represent the 3 chlorides in the formula. Okay, all right. Let's see one more example. Okay, this time it's going to be a little bit complicated. How about this one? Well, how do I know this? When you have Mg and nitrogen N, how do you know when you combine them, it will give you this formula? Well, let's just go through them one by one. Okay, magnesium, okay, Mg would be 2 plus. For N nitride would be 3 minus. So you start from the 1, okay? Each ion will just have 1 ion themselves. Okay, apparently if you just combine these two, the charge won't be balanced, right? So you have to think about how many ions you should have for the 2 ions. Well, how about 2 nitride? Okay. Well, if you have 2 nitride, then total you would have 6 negative charges. In order to balance the 6 negative charges, it looks like you need more Mg2 plus. Would 2 Mg2 plus balance the charge? Well, now you have 4 positive charges, 6 negative charges, not balanced. So you need more Mg2 plus, right? Okay. Now, when you have 3 Mg2 plus, you have 6 positive charges. Now you have 6 negative charges. Well, if you combine those 3 cations and the 2 anions, okay, the charge will be balanced. And when you have 3 Mg2 plus, you write the 3 on the lower right corner of the Mg to indicate how many ions you have. For the 2 and 3 minus, 2 is right here, tells you you have 2 and 3 minus. Okay. All right, this is the part 1 of the naming of ionic compound.